Okay, so I want to go through one more example of our epsilon delta proofs. And remember, the whole idea of an epsilon delta proof is to make sure that if you claim your limit value is a particular number, how close do you need to get to that number, to that y value, so you can guarantee that yes, the limit does equal that number. Like if you were to like cross out that one value, is it trending to that point from both sides? So if that's the case, like how close do you have to get to guarantee that yes, that's the number that's truly there? So like if I'm saying, okay, evaluate the limit as x approaches 1. So, if you directly substitute 1 in there, we can claim that that limit is equal to 5. Okay. And so if we want to get that limit, then we'll go ahead and take this expression and notice that like we're first choosing epsilon just to be that 1/100th. So that's kind of like the given. It's not a general one. So I'm going to say, okay, I have my function f of x minus my limit value of 5 is less than 1/100th. And then we could go ahead and substitute what that is. That's 4x plus 1 minus 5 is less than 1/100th. And then we could simplify that to 4x minus 4 is less than 1/100th. And now I'm going to divide out of 4. So I'm going to take out that 4, factor it out, because remember, I'm trying to create a distance around the limit value, which is 1. And so this is our goal right here. And it works out really nice when you are, there's my highlighter. It works out really nice when you're linear, but we want this right here. That much right there is that's our goal. We're trying to create that, the distance away from 1, an arbitrary distance away from 1, because 1 is the value that we're approaching. Okay, excellent. So then I'm going to divide out that 4. So I get x minus 1 is less than 1/400th. And as soon as I can establish that, then I know that that becomes my value over here, becomes my delta. So I can highlight that. So here's your delta. So for epsilon, equal 2.01, choose your delta equal to 1/400th. And again, thinking about this graph, and you don't ever have to do this, but it's sometimes good to visually see this. So like this is the point in question, 1, 5, because we're saying as we get close to 1, our limit value is 5, and it's just a linear function, right? So there we go. Okay. So if I'm claiming the limit value is 5, oops, not crayon, not pen, one more time, highlighter. So the idea here is how close do I have to get to 5 as I approach it in this direction? Remember, that's your, that is your epsilon. How close do you have to get to 5, to guarantee that that limit will exist? And then what you're trying to do then is choose an appropriate, go yellow. You're trying to choose an appropriate delta, which is on the x-axis. So, and you kind of are working backwards. So your goal is to get within this range of y. So if that's your goal, you sort of work backwards, say, okay, to guarantee that to happen, I need to be within this range of my x. Okay. So hopefully that epsilon delta makes sense. And then maybe we can choose, let's try one more here. So we're approaching -4, and notice it's looking for any arbitrary, oops, I thought I had the highlight. Let's try one more time. Any arbitrary epsilon, okay? So we're going to start off with, just evaluating the limit kind of off to the side. So we are saying the limit as x approaches -4. Oh, it tells you is 1. All right, so that's excellent. That's our L value. So then we start with saying, okay, f of x minus L. We want that to be less than any arbitrary epsilon. And if that's the case, as soon as we know what that epsilon is, we will say, okay, based on the epsilon you give me, I'm going to choose this delta. So I need to figure that relationship out. So my function 2 minus x over 6 minus my limit value of 1 is less than an arbitrary epsilon. And then this is like 2 over 6 is 1/3 minus 1/6 x minus 1 is less than epsilon. 1/3 minus 1 is negative 2/3 minus 1/6 x is less than epsilon. Now, if you're getting stuck, think about what you're trying to create here. You're approaching -4. So your goal, remember, your goal, change the color, sorry, is to get x less than that, or sorry, x minus that limit value of -4 to be less than delta. So you're trying to create this inside to be an x minus -4. So what I can do is maybe just manipulate that. So let's factor out a -1/6. Watch what happens. I think it was orange. So if I say, okay, take out -1/6, put the x here first, is less than epsilon. Well, if you do -1/6 divided out -2/3, you get +4. Okay. And you can factor out that -1/6. When you bring it outside, it just becomes positive, right? You're taking out a -1/6 out of the absolute value, or think about it like this, like, oh no, I mean like that absolute value makes that positive. So I'm going to take out that 1/6 and we get x plus 4 is less than epsilon. Multiply that 6 over, which is kind of unique, less than 6 epsilon. And then if you want, you can say it's x minus -4 is less than 6 epsilon. So we're done. We've created the distance, the space on the x-axis. So if you are at, you're looking at the x minus this -4. So we're approaching -4 on the x-axis. Whichever, whatever size epsilon they give you, you're going to choose this value right here to be your delta. So if you choose, let's say you say, I want to be like 1/100th away for the epsilon, that means your delta is 6/100ths away. You just have to be 6/100ths away and you'll be guaranteed to get that value. If your epsilon is only 1/10, then your delta is 6/10. If your epsilon is just any epsilon arbitrarily, then your delta is 6 epsilon. So really, this is what we're looking for. Given any epsilon that's greater than 0, choose delta equal to 6 epsilon. That'll guarantee your limit to exist. And again, thinking about it from a graph, you're approaching -4, and we said the limit was 1. So 1, 2, 3, 4, 1. So again, here's our hole, and I don't know if it's like a negative slope or what, but that's fine. So we're saying if you are trying to find that limit, so here's your given epsilon. If that epsilon, whatever that distance is, that means you have to be within a certain range of values on the x-axis. Oh no, my battery's low. Okay, perfect timing. The video's over. All right, so and I'm hoping like more examples we go through. Obviously, the the better we're gonna get with doing these proofs.